Hey everybody, we're going to talk about some net ionic equations today. What they are equations that include only compounds and ions that undergo a chemical change in a reaction in aqueous solution. So what that means is that there's other parts of these chemicals that seem to be there but they're not doing very much. So in other words, they're kind of watching the action go down. And if you think about any sport, there's players and there's spectators. And these chemical reactions are going to have the same thing going on. Now, in order to get a net ionic equation, there's three major steps that are going to get us there. Number one, we're going to have to be able to translate a word equation into an overall formula equation, which means translating names of chemicals into formulas for those chemicals. Number two, what is the ionic equation? So if there's ionic compounds in our set of chemicals that come in one of these reactions, we have to be able to split them up into their positive ions and their negative ions. And lastly, number three, we have to figure out what the net ionic equation is by going ahead and canceling out spectator ions, which I'll show you how to do as well. So let's get to it. There is a reaction that takes place between two what almost appears to be water-like solutions, this one and this one. One of them is potassium iodide, and the other one is lead to nitrate. So what we would do in a case like this is we would have to first come up with the formula equation. Now, potassium iodide's formula is Ki, and that is aqueous. We have lead to nitrate, and that Roman numeral 2, remember, that goes with a 2+ charge of this lead. So with nitrate having a 1- charge, it's going to require two of them in order to have a properly balanced compound. Now, this particular reaction, here's a two-part chemical, here's a two-part chemical, both of them starting with metals, tells us that this is the type of reaction that would be classified as double replacement. And in a double replacement reaction, the anions trade places. So the rear ends of these two particular chemicals are going to swap. K will now be followed by NO3, and Pb with a 2+ charge is now going to be followed by iodine, which has a 1-, so we're going to need two of them. Now, what we're going to have to do here is we're going to have to figure out with these products, are they both soluble? Okay, because what we want to do is we want to identify which one of them is going to be our, in this case, our precipitate, our yellow compound here. And that's going to help us to determine our net ionic equation. It's going to be part of what helps us. So actually, let's go through all four of these and we'll see what's aqueous and what isn't. And that will really help us write our ionic equation, which was step number 2. So if we take a look at, let me go to a different slide that has a table on it. And right here, our first chemical was potassium iodide. Here's potassium, and it meets iodine right here. So that is an aqueous species. We had lead to nitrate. Here's lead 2. And if I go all the way across to nitrate, that's aqueous as well. KNO3 is potassium nitrate. That meets right here, aqueous as well. And the only one that's left over was that lead iodide. Here's the lead. Iodide is right here, so that one is solid. Okay, now these four things, having 3 out of the 4 being aqueous, is going to help us big time. And let's take a look how and why. Okay, so being aqueous means it's going to split. It's going to split into its respective ions. So we're going to have K+ here, which is aqueous. Actually, even before I do this, let me take one quick look at this and make sure that I'm balanced. I see an I2 on the right-hand side of the arrow, but I only see one here. So I'm going to throw a 2 out in front. And that changes my number of K, so that's going to make me put a 2 here. Now I got NO3, I got 2 of them, and I have 2 NO3s there. So now it looks like I am much better balanced. Okay, so I can continue on. I'll split K and I into their respective ions. So K+ aqueous, I- aqueous, and there's 2 of them, so I'm going to throw a 2 out in front, 2 out in front. And the lead nitrate we said was also aqueous, so we have a Pb with a 2+ charge, that's aqueous, and I have 2 nitrates, 2 NO3s, which are aqueous as well. Now, on our product side, we have potassium nitrate, this one here, which we said was aqueous as well, so that's 2K plus ions. And we also have 2 nitrate ions, NO3 minus. Okay, and that is aqueous as well. The only thing that's not aqueous was this PbI2. That was a solid, which means that is our precipitate. So how do we go from this ionic equation to a net ionic equation? Well, that's pretty easy. All we really have to do then is we take a look at our ions, and wherever you see the same ion on the reactant side and the product side, we get to cancel it out. So for example, 2K here, and I have 2K here on that side, so those go away. I have 2 NO3 here, and I have 2 NO3 there. That goes away. So really, all I'm left with now is the things that aren't crossed off. So I have, in my net ionic equation, I have 2 I minuses, and those are aqueous. There we go. I have a Pb2 plus ion, aqueous as well, and that will yield our product, which is PbI2. And that's a solid. In this case here, we saw it's this yellow colored solid in that particular reaction. So, what we saw with the canceling out was this potassium here, this nitrate, they're just spectators. They're not actually involved in the real net reaction going on here. Overall, what these two chemicals mixing together gets you is lead iodide. So in this case here, what's left are the most important things that produce this particular precipitate product. So again, 3 steps. Translate your word equations into chemical equations. 2, take those chemical equations here, translate them into ionic equations, and make sure you check a solubility chart so you know which ones are aqueous and will split apart from each other. And then lastly, cross off your spectator ions, those found on both the reactant and the product side, and what you're left with is your net ionic equation. So I hope this helped you understand this concept a little bit better. It takes practice to get good at this particular one. Good luck, and I'll see you next time.